Hey everybody, so thanks for coming out today. The seminars have been awesome this weekend, so I'm really honored, and thanks to the organizers of the show for asking me to come out today. My name is Lindsey Rupertus. I'm going to talk to you today about basic solid-state pinball repair methodology. So I was asked to come speak again this year, and I was told I could, talk about basically whatever subject I wanted to talk about. But Richard recommended I do basic pinball repair methodology, so I figured I'd narrow it down to solid state. That's more my area of expertise, and to try to cover electromechanical games as well in 1 hour was going to be really difficult. So I'll just start by talking a little bit about who I am and why you should care about what I have to say about solid state pinball repair. So this is one of my sites. This is, you could say, my blog. It's warpzonearcade.com. Some of you may have seen it. This is another one of my sites, pinforge.com, where I sell some of my circuit boards and things like that. So actually, before I go any further, I should probably mention that if you guys have any questions, feel free to jump up to the microphone there and just say, hey, I have a question. Because last year I realized I tend to end up looking at the screen a lot and miss out on questions, and I'd like to make it interactive, so feel free to do that. I also wanted to announce today that anybody here that's maybe bought some of my products may have realized that I'm good at designing and building pinball circuit boards, but I suck at dealing with customers and shipping orders. So I've teamed up with Todd at Big Daddy Enterprises. I'm sure some of you guys are familiar with that. So he's going to be reselling my stuff for me, so you don't have to deal with my slow shipping or lack of communication because I've gone on vacation or something like that. So I've also developed some test aid circuit boards for different pinball systems. So here's an example of one that I developed for the Ballystern NPU. I also developed some other stuff like an LED board for that system. Here's an example of me doing some hacking to come up with some of these ideas. And then here's an example of single EEPROM conversions that I developed for the Ballystern system. And I've actually got this stuff on PinWiki now. I color-coded the wires and stuff to make it easier to follow. Now, I didn't obviously invent address decoding, but I came up with my way to do these conversions and documented it. I was also interviewed on the Silver Ball podcast with Rob and Steve. Those guys are great. And I was here last year, and that's such a great poster. I also just wanted to share quickly a couple pictures with you guys of different warehouse raids I've done over the years. I have some notes, I guess I should probably pull those out. So I've been collecting about 13 years now, and that time I've owned several hundred games, maybe about 300. I currently have about 80, and recently I got down below 100, and I'm really working to stay there. So I've also been quite active in online communities like KLOV and to a lesser extent RGP. RGP is the kind of thing where there's a lot of guys there answering questions that don't really need my input from time to time. But KLOV is a forum where I've contributed a lot, and in fact, it's a good way to build your skills because I learned a lot about pinball helping other people. There was a couple years there where virtually a daily basis I'd be digging into schematics and manuals to try to help out other collectors, and then as a consequence I learned a lot myself. So helping your fellow collectors is also a good way to learn. So this is just some warehouse raid pictures. This was a really interesting one. They had this big hangar, and they built this second floor, and it was all rickety, and they had like hundreds of games up there. There's a bunch of cocktail tables, some more pictures. They had maybe 500 video games in there, just an amazing find with some really rare titles. Unfortunately, a byproduct of that type of operation is you run into this kind of stuff too. So I actually rented some storage from the operator that owned this building, and from day to day I would come by and I would witness these kinds of scenes and this stuff going into the landfill. So that was kind of a bad scene. Here's one of my prouder moments. I loaded these three into this quarter-ton truck by myself, and if anybody's ever dealt with these games, you appreciate what kind of accomplishment that actually is. And I moved them, I took a 3-hour drive with them So that was quite a day. And I came back, I can't remember what I came back with. It was something pretty good though. So back to the crux of the whole thing. So where do we start? So isn't it obvious? The internet. The internet's going to be, you know, obviously your greatest source of information for pinball. There's an amazing community of people out there, people way more motivated and intelligent than myself who are more than willing to help you out. Keep in mind too, it's just switches, solenoids, and lamps. I mean, you have sound, display, and a power supply, but at the core of it, it's just switches, the MPU sensing what you're doing by the switches, and it's controlling the solenoids and the lamps. So, you know, don't overcomplicate it unnecessarily. Keep it fun. That's something I really talked about this weekend with a lot of people. That's really important. It can become not fun really easily. So some examples of ways that can happen is if it starts becoming too much like a business. I was mentioning I owned several hundred games, so at that point, it's gone beyond hobby. I would call it a hobby, and people would say, I don't think this is a hobby. So, and as a consequence, there was some stressful times, and I could do a whole presentation about how to make pinball not fun. So don't do that. Learn as you go. I mean, you're always learning. And push yourself, but know when you're in over your head. And that's probably the most important piece of advice I can give you today, is know when to stop. And be honest with yourself about what you know, and that's how you learn. A lot of times people will put up walls to their progress by assuming that they already know it. So some problem solving. I want to just talk about some basic problem solving strategies. So I've boiled it down to really the most core extremes. So we have a rules-based approach, which is for a given problem, you use a predefined solution. So you have a broken game. You go to the internet, you say, okay, this guy had that same problem. I'm going to apply that solution and hope that it works. And then at the other extreme, you have a fundamental understanding approach, which involves using test equipment and having a complete understanding of how the system works. And then you can use deductive reasoning and logic to solve the problem. So in the real world, we're going to have a hybrid approach, and in the a combination of both. And in the past, I've really been a supporter of the fundamental understanding approach, almost to a snobbish level. And over time, I've really realized that any of these approaches are valid, and it ultimately comes down to what you want out of it. Maybe you don't want to know how a pinball machine works. Maybe you just want to fix your game. That's completely valid. And this really came home for me. I had a friend of mine working with me. She wanted to buy a game. She was just finishing university and she didn't have a lot of money. So I agreed that she would come and work on games, and then she'd work off the machine, take it home. So one day she was working with me and she was trying to fix Stern's soundboard. She's really smart. She's a master's degree in mechanical engineering, so I give her a lot of credit for being really smart. And I was telling her, well, you should learn about Motorola 6800 series computing systems, and you should learn about oscillators and timers and address decoding. And she just said, I don't have 2 years to fix the soundboard, so just tell me how to fix it. So then I really realized, this is a valid approach too. So one concept that I like to apply to problem solving is split the problem in half. So you're not necessarily going to be able to apply this to every problem. It's just something to kind of keep in mind and use. So if you logically think, I have this problem, if I'm able to do some basic testing or reasoning and break this into 2 chunks, and now I can say, okay, the problem exists over here, you've now just eliminated 50%. And then you can split that down and split that down. So this isn't an innovative idea, but it's something to keep in mind. Obviously, this person's taken that a little bit too literally. And don't get overwhelmed trying to consider everything at once. That's a problem people can run into as well. And these two things kind of go hand in hand. And then when in doubt, you can apply a known procedure, and that goes back to the rules-based approach, which I discussed earlier, which is valid. And like I said at the beginning of the presentation, there's a lot of really knowledgeable people who can help you out and give you that kind of approach. So I also just wanted to talk a little bit about the concept of best practice, which it's a buzz phrase. I mean, that's why I included this Dilbert cartoon. But the idea is that It's a technique that is, this is from Wikipedia, so a technique that has consistently shown results superior to those achieved with other means and that is used as a benchmark. In addition, a best practice can evolve to become better as improvements are discovered. So really what that means is over time you're going to develop a set of rules for yourself, you could say, but it's not the same as using a rules-based approach to your problem solving. So the concept applies more to implementing your solution to the problem rather than actually determining what that problem is. So one example of a best practice would be replacing filter capacitors in a power supply or something like that. And just to keep that concept in mind is important because it provides you a framework of useful problem solving. I am going to get to actual pinball repair. I just wanted to set up some, important ideas. So, some fundamental concepts that are going to be required to actually repair pinball machines. Obviously, you're going to have basic knowledge of electricity. You're going to need a basic knowledge of digital electronics. It's also important to understand the modularity of systems in a pinball machine and realize that a pinball machine really is just a whole bunch of systems stuck together to make one thing. I mean, that's true of most electronics or even this chair. It's a combination of stuff stuck together. But if you think about it in those terms, it becomes somewhat less daunting. And the interconnectivity of those systems, that's really important to consider as well. So you'll need some knowledge of electromechanical components like switches, relays, etc. And also mechanisms, things like flippers and pop bumpers. One of the things that I really enjoy about pinball, which ultimately years ago made me make the move from collecting mostly arcade games to collecting pinball games, is there are so many of these different elements which make it challenging and fun. And the mechanisms and the electromechanical parts obviously are what differentiate the two, and that's part of the fun as well. I just wanted to talk a little bit about safety as well. So safety is something that's really important, obviously. Don't get complacent about safety. That's one of the other most important things I can bring to you today. Try to unplug the machine whenever possible. Even if you have it turned off, you still potential there to get injured. Avoid working with the power on when you can. That's obvious. Remember that the thing can hurt you. Always remember that. I mean, you could get hurt by a pinball machine for sure. And use common sense. I mean, that's pretty obvious. And when you'll get complacent about safety is when you start to get comfortable. That's probably your most dangerous time in terms of working on anything that can become dangerous, is when you're comfortable with your skills, you start to get a little bit complacent. That's the time when an accident's going to happen. So manuals. Manuals are really important, obviously. Don't overlook the original manuals. Many are available online. Originally, when I started working on games, I mostly used pin repair. I forget, that was Marvin 3M back in those days. And I just kind of overlooked the original manuals, and then I discovered stuff like this manual right here, the Bally Electronic Pinball Games Theory of Operation. And this was really a breakthrough for me in terms of understanding how pinball actually works. So I would recommend to anyone to actually read this. It's written in such a way that you can understand it. It's kind of like A Brief History of Time by Stephen Hawking. You can understand complex physics just at a layman level. Not that pinball is even close to that complicated. And keep in mind, you can also cross-reference these manuals. So pinball systems are common from game to game. So if you can't find an Elvira and the Party Monsters manual, maybe a Taxi manual will have the information that you need. So keep that in mind. Schematics and data sheets, obviously those are really important. The data sheets are something that I overlooked for a long time as well. So if you're not familiar with what that is, each of the chips on a board, so here we have a Stern MPU schematic. So this is a 6821 PIA, for example, and this is the data sheet. So what the data sheet does is it just goes into explicit detail about how the thing works, the pinout, those kinds of things. And that actually will really give you a window into the the fundamental understanding approach to problem solving. Reading this intensely boring data sheet really gave me another window into how this whole thing works, like how this works. How does the CPU actually configure this thing when the thing boots? All those kinds of details are important. Schematic symbols, so some of these are going to be intuitive, like a switch. I mean, that's fairly intuitive. Some of them are not, like the gates, the logic. I mean, just looking at that, you'd have no idea what it is, but understanding and reading schematics is critical. I'm not going to go into great detail today. Also, IC pin numbering. I'll just basically go over this. So you have the notch here. It starts at 1, goes down, and then carries on this way. It doesn't go back and forth or, this way, that way. That's something that's really important. Tools, basic tools, obviously, you're going to need. A power supply is important, like a bench supply. When you're going to be working on electronics, especially digital electronics, you're going to want a +5 supply. So that's a good thing to have. And you can find PC power supplies practically free. I mean, here we can see these are probably destined for the landfill. A good meter is really important. I like this meter. It's really cheap. You get what you pay for, but it's 10 megahertz oscilloscope, and it's under $200, so you can get some fairly good test equipment for reasonable pricing these days. The logic probe. Logic probe is going to be important with digital electronics too. It connects to the +5 volts, and then you can probe into the circuit, and it will tell you what you're connecting to. So either high, which will be +5, low ground, it'll be strobing. I'll go a little more into that as we go along. EEPROM programmers and erasers, those are going to be really important as well. So the power cord, that's where we should start. A lot of people will overlook the power cord, and I've done it myself. So you'll get a game that comes in. Maybe this prong is broken off. Maybe your cord looks like this. You plug it in, it works, everything's fine. But you don't want to end up in this kind of situation. And some of you guys have probably experienced where you lean your arm across 2 games across the lockdown bars, and suddenly you feel electrocuted. So that's one of those games likely does not have this prong. And it's kind of funny and trivial, but in reality, that could result in your death. I mean, it's unlikely. You never know, right? Better to be safe than sorry. Here's an example of a game from my collection that was involved in a fire. Power cord problems can cause that kind of damage. And you definitely don't want to get electrocuted, because you'll end up looking like these guys. So the onboard diagnostics, in fact, all solid-state pinball machines are going to have some kind of onboard diagnostics. That's probably a good place for you to start with the game, assuming the game will actually boot and go into the onboard diagnostics, which in many cases it won't. Inside the coin door, you'll see switches that look like this. You can consult the manual. It'll tell you in much greater detail how to actually use that stuff. So now we're getting into this little more interesting stuff now. So I talked earlier about the modularity of pinball machines. So here's some examples where we've got, this is a Williams System 3 through 6 game. We have the MPU, we've got the driver board, we have a sound board, we've got the power supply, and just, it's important to think of those things as logically separate things that talk to each other. So here's a Gottlieb System 3 game. Again, we have the MPU driver. This is the sound dot matrix driver. But you see all these cables interconnecting all this stuff. So it's important to think about how do these things talk to each other. And that actually can lead you to some very easy problem solving. Like I've had lots of Bally Stern games where problems have happened, and I've almost immediately been able to track it down to a bad connector pin just based on knowledge of how these things talk to each other, and the consequences that can occur when one of these signals might drop out. So input and output. I just wanted to talk about the concept of the MPU having inputs and outputs, meaning it's doing things like sensing switches that would be an example of an input. It's doing things like driving solenoids. That's an example of an output. So just keep that concept in mind. Fuses, fuses are an easy first troubleshooting step. Just check them all. You want to ensure that you have no overfusing. That's really important when you get a game, and this is something I overlook constantly, but you want to make sure that the fuses that are installed in the game are actually the correct rating, because if somebody's taken a 20 amp fuse and stuck it in a 1 amp circuit and something shorts out, now traces are burning off circuit boards and smoke is pouring out instead of the fuse blowing. So check the manual for the ratings. A lot of times it will say the ratings right on the board. This is an example of a rectifier board. And also keep in mind that the fuses can be all over the game. Like some games will have fuses in weird places under the play field and things like that. So I wanted to just talk about the basic concepts of AC and DC voltage. So we're not going to talk about the iconic rock band or the awesome pinball machine. We're going to talk about alternating current and direct current. So just to give you a basic overview, these two graphs here show the voltage on the y-axis, and the x-axis will be time. That's not represented here, but just keep in mind that it's time. So with AC voltage, the voltage is going to go up to a positive, it's going to cross 0, it's going to go down to a negative, and so on and so forth at a certain frequency. DC voltage, it's just positive. It's just positive, or not necessarily positive. It's not oscillating. It's just fixed. And it's just, through time, it's maintaining the same number. Transformers. Transformers are a good place to start in terms of understanding basic pinball concepts, because that's the next thing that comes after the power cord. Effectively, the power cord is just plugged into this sucker. And logically, you can think of a transformer as like a voltage converter. So voltage is going to come in, and one or more voltages will come out based on the ratio of that transformer. It's important to also remember transformers operate only on AC voltages or pulsed DC. You can't just apply DC to a transformer and get a ratio of that DC out. I won't go into great detail about how they actually work, but just keep that in mind. So it's a voltage converter. It's also important to consider batteries. Batteries are a really important thing in pinball. I'm sure a lot of you guys have experienced this type of scenario where you have corrosion and your circuit board is just melted here due to a battery that's leaked. So it's also, when you're doing these kind of repairs, important to consider what type of battery was in the game, because if you have like a nickel cadmium battery, for example, you can use an acid like vinegar to neutralize it. But if you have just a regular like alkaline battery, that's going to have an acidic acid. So adding an acid isn't going to neutralize anything. You're going to need a base. Go back to elementary school with the litmus paper and the pH scale. So there's also a solution to the battery problem, which is using an NVRAM adapter, which basically you take the RAM out of the game, you install this RAM, which no longer requires battery backing in order to actually maintain the memory. So what's happening, this RAM here is where all the settings and all that kind of stuff are stored. And typically when you turn the game off, this RAM is still running, powered by these batteries. So this RAM's just running all the time. In this case, you don't. And I'm going to, I build these. I'm not the originator of this idea, but I'm going to give out a bunch of those at the end. So come up and see me if you want one. So diodes and just semiconductors in general is another really important concept to understand in terms of pinball repair. So we'll talk about the word bias. So bias is a term that describes when the diode is actually conducting. So when it's turned on, that it would mean that it's biased. And different diodes are going to have different voltages. I guess I should start by explaining a diode is a semiconductor which will allow current to pass only in one direction. So here's a fairly simple schematic. This is a basic seminar, so you don't necessarily need to know how to read schematics or understand schematic drawings, but I am going to use some schematics and I'm going to try to explain it in a simple way. So we have a voltage reference here. Here's the positive side, here's the negative side, and we can see currents flowing through this circuit. There's two sides to diode. In fact, these are all LEDs, but it's just easier to demonstrate a diode. It's just a kind of diode where light comes out. So you have two sides to the diode. They're called the anode and the cathode. And when I was in trade school, probably about 15 years ago, one of my instructors told me to remember this, because if you don't like cats, then it's a negative, and that's the negative side. And as lame as that is, today I still remember that. So in this case, if we reversed this, no current would flow through here because this diode would then be blocking. So that's an important concept to understand. If any of this, like, if any stuff's not making sense or you need a little bit more explanation, feel free to just jump up to the mic. So the power supply. So the power supply is the next thing that's going to kind of come in line after the transformer. It's the lifeblood of the game, you could say. It's the thing that supplies all the voltages out to the different systems. Pinball requires a number of different voltages to work. I just wanted to show you guys this fairly basic linear power supply schematic. This is from a Williams soundboard. There's different kinds of power supplies. There's switching power supplies. This type of power supply is called a linear power supply. So it's important to just understand the concept that we have an AC voltage, which will come to the power supply. We have what is called a bridge rectifier, which is a series of diodes, which will then produce DC at the output. And if you looked at this in greater detail with the understanding of how these diodes conduct, and you look at the AC waveform coming in, it'll make sense. DC comes out. And then over here you'll have, typically you'll have a regulator. So what that will do is it actually regulates the voltage to just make it consistent. You may have some variability here. In fact, you will have variability here. And this is a capacitor which is connected in parallel, which does the filtering. So I'm going to talk a little bit more about capacitors. Yeah, okay. That's a good question. That's a really good question. So 12 volt unregulated, where will that be used? Typically, 12 volt unregulated is going to be used for audio amplification circuitry. So in that case, having a constant voltage is not necessarily required, because what's going to happen with an audio amplification circuit in this context, adjusting that voltage is really only going to make it louder or quieter. So it can tolerate, those circuits could tolerate voltages, say, from 8 volts to 14 volts. So the short answer is they don't need to regulate it in order for it to work effectively. And then if you're looking at regulated circuits, such as this is a 5 volt voltage regulator. It's extremely important that you have a constant 5 volts within a small variability in order for the logic to work properly. So I'm going to talk a little bit more about logic as I go, and it'll make a little more sense. Well, not necessarily. I mean, there's certainly cases where I can't think of a great example of another alternate usage for that, but something like lighting, like illumination, something like if you were going to do maybe a zero cross circuit against an unregulated, unfiltered DC. The next slide, I think I'll explain this a little bit more for you guys. So capacitors. Capacitor, logically, you could think of it as a battery. It stores electrons. When there's a voltage applied, when the voltage goes away, it discharges and those electrons go away. They flow out. So some are, well, not necessarily, actually. You could charge a capacitor, take it out of the circuit, the electrons are still there. I shouldn't confuse you guys. So There's different types of capacitors. Today I'm really only going to talk about electrolytic capacitors. They're called electrolytic because they contain electrolyte, much like a battery. These things have a finite lifespan. Here we can see a Gottlieb System 1 power supply with these big capacitors. Once these capacitors exceed their lifespan, it's time to replace them. So I was talking about best practice earlier. This is the type of thing that you could consider a best practice. They get old, you replace it. Even though the game may still be working, at some point in the future it will stop working. And you can get things like resets happening, especially with WPC games and even newer games. You can have resets that strictly boil down to the fact that this capacitor has gone out of spec. So I just wanted to talk a little bit about how these capacitors work in a filtering capacity in a power supply circuit. So I talked about the rectification in the previous slide, full wave rectifier. That's what this thing is. That's the thing that takes the AC and converts it to DC. But what happens is you've got this converted to DC, but all it's really done is taken the waveform and kind of flipped it over. It's taken the bottom half of the waveform, flipped it over onto the top, making it a positive. So if you were to see that on an oscilloscope, you would see it. It looks like this. This is a DC voltage, but it's still got all these humps here. So in a pinball machine, they'll have a capacitor in parallel with that voltage, and what that will do is, you can see on this, when it's charging, when the waveform's going this way, it's charging the capacitor. When it starts to drop off, now the capacitor will discharge, and then your waveform starts to look like this. So we can see capacitors charging as it comes up. It's going down, now the capacitor's discharging, and it starts to look like this. So you've gone from quite lumpy to not very lumpy at all, and that's how that works. And it's, again, it's important in logic circuits to have this consistent flat voltage, because the CPU, like the computing element of the whole thing, is using this as its reference of a 1, a binary 1 or 0. So if it's like a 0.5, that's not going to work. The thing's going to, what they call, run off into the weeds and just start going crazy. So logic, the concept of logic, 1s and 0s, binary, this is going to be an important concept in the world of pinball as well. I mean, you can certainly get by without really deeply understanding this, but it's important to understand that from a binary perspective, plus 5 volts will be called high, which is also a binary 1. Ground will be called low, which is also a binary 0. So the computing system inside the pinball machine is operating at a binary level. These are the binary references. So again, the signal's traveling around in the game. I think with this slide I just wanted to kind of really hit home that, you know, remember that there are stuff, the MPU is talking to all the other boards, and in fact the other boards may be talking back to the MPU. So it goes beyond just the component level stuff. There's interconnects, there's connectors, there's all kinds of issues that can happen independent of the actual PCBs. So the MPU, just keep in mind with the MPU, it is a computer. It's, you know, it's not unlike a personal computer in the sense that it has ROM, it has RAM, that kind of stuff. So the switch matrix. So you've probably, if you've been around pinball, you've probably at least heard this term. So I'm just going to explain a little bit how the switch matrix actually works, and how the MPU actually senses switch closures. So you have your switches laid out in what's called a matrix. You've got rows and columns. This is a concept that applies to lots of different things. But the way this will work is these, let me just make sure I get this right. Yeah, so all of these lines are connected to the MPU, and what the MPU is going to do is, one at a time, let's just assume we're in a rest state. All of these are connected to ground. These will just all connected to ground. So the MPU is going to come along. It's going to apply a high signal here, which is +5. And then it's able to use these as inputs. So now we're sensing this series of switches. So if we apply +5 here, this one's closed. We can see this is the cathode side of the diode, so it will conduct. We'll have +5 through here into here. The MPU senses that and says, okay, this switch is closed. Does the same thing here, and so on and so forth. And then what it does is once it's done this one, connects this back to ground. This one now is connected to high. Now we've sensed all these switches. And what's happening is it's doing this at such a rate that it will catch the switch closure. And for me, when I first started learning about pinball, this seemed kind of like a weird concept because that switch closure is happening like so fast. I mean, the switch is closed for maybe microseconds in some cases, but then you realize, well, this thing's operating hundreds of thousands of instructions per second, so you know, logically you can realize, sure, that's happening easily fast enough to sense that switch closure. And in fact, what will happen is it may even come back multiple times while that switch is still closed. And then you get into a concept which is called debouncing, which basically, just to put it simply, it's the way that the MPU deals with potentially switches that are closed, or in fact, that specific term deals with switches that are opening and closing like quite quickly, because when you hit that switch, you might not see this with your eye, but there might be a period of kind of you know, action-reaction stuff going on where that back contact is kind of bouncing. So that's what the debouncing is. And you'll see there's an example of it here. There's a capacitor across the switch, and that's one way to debounce, because now what will happen is when this closes, this capacitor now gets charged, and then when this switch is open, there's still a high signal here for the time that it takes to discharge this capacitor. So that's one way that Bally games, Bally Stern games, that's how they've achieved their debouncing. So that's important to keep in mind, because if one of these capacitors now becomes shorted, this switch appears stuck on, right? Because now it's like you've just stuck a wire across here permanently. So switch matrix. Does that make sense to you guys? Any questions? So there's another matrix that you'll find in pinball machines, the lamp matrix. The concept is exactly the same. You have stuff laid out in a matrix, except in this case, we have lamps now instead of switches, and instead of sensing, we're actually going to be driving the circuit. So what will happen is the same sort of situation. All of these will be connected. I didn't look at this one in detail, so we'll just say to ground, and then one at a time, it will drive that column of lamps, whichever one needs to be on, and then it goes to the next one, next one, next one, and so on. So it's happening so quickly that you can't actually perceive that with your eye, even though the lamps are not necessarily being turned on all the time, even though you perceive it to be on all the time. I'm going to talk a little bit more about how vision works and perception and how it relates to pinball more later. So some games don't use a lamp matrix. This is an example. This is a Stern schematic for the Stern lamp driver. You don't need to understand all this. I just wanted to demonstrate the concept that that game actually has, or those games, has individual outputs for each lamp. So the benefit, I guess we can talk about the benefit of the lamp matrix or switch matrix, and why would you do that? Well, it's kind of obvious, because you're able to drive all these lamps with only this many wires, right? In this case, now you've got all these wires just from a manufacturing and cost perspective. And so general illumination, sorry. General illumination. You guys are probably all familiar with that. Those are the lights that come on when you turn the game on. A lot of times when people have a game that's not working, they'll tell me, well, I turn the game on and all these lights come on, but the thing just doesn't work. So general illumination typically is a fairly simple circuit, and here's an example of the most simple, really. You'll have a voltage coming off of your power supply. Typically that will be rectified but unfiltered DC voltage, AC actually in some cases. Anyway, you have a bunch of connectors, and then it just goes out to the lights, and there you go. So a really common thing, probably the most common thing you'll encounter with pinball games, is connectors being burnt, such as this, in the general illumination circuit. So what happens is, as you can imagine, those lights are just burning away all the time. So if the game's on for hours and hours on end, over time, these connectors will heat up and they'll fail. And certain series of games like System 11 and WPC and newer games, it's virtually inevitable that you'll find this kind of thing if these haven't been repaired already. These IDCs, if we had Dave Okert here, he could tell you how much he hates these kinds of things. Next, I wanted to talk a bit about coils. Let me see, how's the time? Okay, we're doing okay. A little bit about coils. So here's a here's the playfield solenoid diagram from a Gorgar. And again, I mean, you don't necessarily need to understand all this. What I did want to demonstrate, though, these are all the coils. These are the schematic representation of the coils. Notice that there's a common connection here. That connection is common to the positive side of the solenoid voltage from the power supply. So, and the ground sides are then controlled, CPU controlled. So you have common positive side, ground side is CPU controlled. So this is an example where we can use our split the problem in half approach to solving a problem with a coil. Problems with coils are going to be like the thing's either going to be stuck on or it's not working. There's really no in between as far as a problem goes. So step one, we can go to our coil and use our voltmeter and see, do we have this side? Is this here? This positive side coming straight off the power supply. If we do, then we've just split our problem in half, right? Here's our problem. We know our the source of our problem. We know the solution lies over here now, or over here, as the case may be. Also, keep in mind that there's a diode across all of these coils, and I'll try to just quickly explain the purpose of that. So, the coil, it's obviously a bunch of wire, and when it's energized, there's going to be a whole bunch of electrons running through here, and then when we take the source of current away, those electrons are still in there. So where are they going to go? So what happens is they try to run out of the coil going in the current flowing in the opposite direction. They come in flowing one direction. When you take the current away, they flow out going in the other direction. So this diode, when this is energized, it won't be conducting. It'll be blocking. And then when you take the current source away, all these electrons are trying to go somewhere. So this will conduct and essentially absorb that. So if you've ever taken a look inside of a coin door when you're flipping a game, you'll see big bolts of lightning shooting out of the flipper switches and stuff. That's the source of those bolts of lightning, is this electrons trying to run out of the coil, and it's called counter electromotive force by really old people. Well, electromotive force was the term for voltage before voltage, so counter electromotive force basically is like counter voltage, meaning it goes the other way. That's the way I learned it, though, and I think it's still discussed as counter electromotive force. Well, we'll talk about that after. So I just want to show you guys a typical solenoid driver circuit. So this is what will be hanging off of the other end of these. This is where your ground side of your circuit is going to happen. And this will be where that ground ultimately comes from. But just keep in mind, you have the CPU over here. It's driving this, which This IC is called a peripheral interface adapter, which is kind of a fancy way to say I/O multiplexer, which I guess is a fancy way to say whatever. The point being the CPU only has 8 pins which act as inputs and outputs. Those are called the data pins. So if you're limited to 8 inputs and outputs, you're not going to be able to build a very good pinball machine. So what these do is multiplex those outputs. So just understand that in concept. And that allows the CPU to drive through this pre-driver circuit, drive this transistor, which ultimately, when this is turned on, ground is, current is flowing through here and then out to here. So what we can do then is this transistor, typically in a pinball machine, is going to have a metal tab connected to it, which will be common to this connection right here, which is the one going out to the coil. So here's an example of the transistors. So what we can do then is manually apply a ground to here, to this metal tab, and what we've effectively done now is we've completed this. And then if your coil now starts to work, well, that tells you that connectivity between here and here is good. So you've now tested through all these connectors, which can be a problem. So now again, you've logically split your problem in half. So you can see we're getting close to the solution. And then if you apply ground there and it doesn't work, obviously you have some kind of problem with those connectors. Now we've isolated to here, and we can get into that, which I won't go into great detail today. Now the coil being that was for a coil that's not working. One that's stuck on, that's a different problem. Now probably something in here is shorted, and it's going to be stuck on all the time. Usually it will be this big driver transistor right there. Keep in mind also in Williams pinball machines there's solenoid driver circuits which are called special, which will basically be a conventional solenoid driver circuit with a switch, which can also just directly drive. What would happen typically is the CPU would sense a switch closure. It would then drive a solenoid appropriately. In this case, the MPU isn't really involved at all. It's just, the switch is just driving the solenoid directly. You'll typically have 2 switches on these circuits. One is for the CPU to sense the switch closure for scoring and those kinds of things. And this will actually drive the solenoid. Now, why would you want that? There's time involved in the CPU actually sensing the switch closure and then energizing the solenoid. So what can happen is those switch closures, like say you have a series of pop bumpers and the ball's just flying around like crazy, the CPU might not actually be able to keep up with that. So what this does is it eliminates it. It eliminates that kind of problem. Gottlieb solved this problem with, you've probably seen pop bumper driver boards on Gottlieb games. That's what this does. Bally, on the other hand, they didn't do any kind of special solenoid stuff. They just relied on the CPU sensing the switch closure and then driving the solenoid. But their concept of special solenoids was done more in software, so I won't go into great detail about that. I'm running out of time. So flippers. Flippers, I mean, it's not much of a pinball machine without flippers. So keep in mind with flippers, the flipper is actually 2 coils. It appears as 1 coil, but there's 2 windings of wire here. And one winding is going to be, well, also keep in mind that this is an electromagnet. I mean, it seems fairly obvious, but pinball machines basically operate due to the magic of electromagnetism. So one of these coils is going to be really strong, and one will be relatively weak. And the strong coil will draw a whole bunch of current, and if it was on all the time, while you're holding the flipper button down, the thing would melt. So once the flipper reaches its end of stroke, there's a switch here called the end of stroke switch. In some cases it will open, some cases it will close, but the point is, what that switch does it de-energizes the heavy current draw strong coil, and it energizes a weaker coil just strictly for the purposes of holding the flipper up. Because once this flipper is up, it doesn't take a lot of force now to just keep it there. So some things to keep in mind about flippers. You've got the coil diodes. They perform the same function as I described with the other solenoids. In flippers, they're fairly critical though, because it is a pretty high current draw and it's a solenoid that's going to be going all the time. So bad coil diodes can cause things like resets and stuff like that. End of stroke switch, I mean, obviously the adjustment's important. Keeping these contacts clean is really important too. And that's true of the cabinet switches as well, because the current is actually flowing through here, and it's also flowing through the cabinet switches in order to power the coil. So you can imagine if these are all pitted and corroded, you're not going to have a good path for current flow. Consequently, you're going to have a weaker coil. Well, it depends on, like, basically what I've described here. This is for older games up to, I think T2 maybe was the last game to use this kind of system, and then from there, they went to a pulse width modulation based flipper circuit. So in that case, you'd have only one coil, and in order to make it adjust the strength, they use what's called pulse width modulation, which unfortunately I don't have a lot of time to go into today, but I'd be happy to talk to you about it after. And yeah, this just basically outlines what I was showing you before. Displays. So displays, some things to consider with displays. Very high voltage, typically. You're using neon and fluorescent technologies. The ones that are using neon, which would look like this, they use very high voltage. Gottlieb uses a fluorescent system, which is like this. So I wanted to talk about the concept of persistence of vision, which is a concept actually that's been kind of debunked, but for our purposes it's easier to explain using this. So if we look at this image of the horse running, we can realize that this is just a series of images which are being displayed in a sequence. But our mind doesn't perceive any of those static images. It perceives it as being a fluid thing, right? So that applies to displays, because what's happening in the game is at any given time, only one of these is going to be lit up, only one of these digits. So it'll light up this one, then it goes to, you know, whatever. But your eye doesn't perceive that. It's doing it quickly enough that it actually appears that they're all lit up at the same time. So the same concept kind of applies to the lamp matrix. And in fact, speaking about the lamp matrix, that's why you can run into some problems using LEDs. Like you'll see they're kind of flashy because the LED will turn on and off much quicker than an incandescent lamp will. So now your eye is able to perceive that strobing of the matrix. So there's solutions to that, but that's why that problem occurs. So I wanted to just show you guys quickly a schematic of a display, just to give you the concept that if we look at each individual digit, realize that each one of these segments is driven by its own driver circuit. So if we look here, we can see these outputs all go out to these segments, and there's a unique driver circuit for each one. So you could have problems where a segment is not working or it's stuck on. So with the knowledge that there's a unique one for each segment, we can go here and say, okay, well, A, which one's A? There's A. Maybe I've isolated my problem now to right here instead of, you know, what the heck's going on. And also keep in mind there's a unique driver circuit for each digit. So if we have one digit that's not working, we can say, okay, maybe it's the 100,000s. So now I've isolated, you know, in concept. It could be something else, but we've tried to isolate it down to that. So relays. Relays are an important concept in pinball as well. And a relay basically is just a switch that's controlled by an electromagnet. So it basically now takes a physical switch and allows you programmatically with a computing system to operate it. So here's just a basic image of what a relay will look like. So these are our switch contacts right here. These are going to go out to whatever. Here's going to be our wire coming in that we want switched. And this is an electromagnet. So we can see now, this obviously is metal. When we energize this electromagnet, this is going to drop down, and now we have a path through here. So it's also important with relays to understand the concept of normally open and normally closed. And normally, what normally means is its normal state when it's not energized. So here's an automotive relay. These are also used in pinball machines. And here's the schematic of that relay. So we can see there's two posts here labeled 87A and 87. So 87 in this case is normally open, which means in its normal state there's no connectivity between here. This terminal is normally closed. So we can see in its normal state, obviously there's, this is kind of not intuitive because this isn't going to push this way, but you get the idea. So you can see cases now where, I can't think of a good example of where you'd use a normally closed, but that's the concept. Where this is used in virtually every, well, in fact, every solid-state pinball machine is a flipper relay. I think I'm going to show that next. So what happens in the case, this is a Stern game, if I remember correctly, old Stern. So what's going to happen is the ground side of the circuit is going to go to the flipper button. From the flipper button, it's going to come up here to this board, and then that is going to pass through this switch, which is actually inside of the relay. So you can see now when the relay is energized, these are closed, and your path to ground now goes out to the coil. So that's how the game is able to turn the flippers on and off. The same is true of general illumination in a lot of games, and there's other examples of where relays would be used, like motor controls, things like that. A relay is also a good way to switch something with high current using a low current type switch. So it takes very little current, relatively speaking, to drive this coil, this electromagnet, which is going to control this. And now we can have really high current contacts here. And we've switched a high current circuit with a really low current. So when we're talking about having logic now, a transistor over here driving this, you'd need a pretty giant transistor in order to handle the current involved in driving the flippers. So I'm getting to the end here. I think I've pretty much on time. Lastly, I just wanted to talk to you about the concept of reset and the reset circuit, something you may have heard about. Now, the point of this, when you turn the game on, you can imagine there's a brief moment in time where the power supply is powering up, right? It might be charging the filter caps. You know, it's getting ready to run. So your CPU now, I explained earlier, is going to need a really smooth and consistent reference to +5 to use for its binary logic. So if the CPU starts running in this area, weird things can happen. You could have unpredictable results. So what the reset circuit does is it actually basically turns the CPU off, and some peripherals and sometimes RAM and whatever else, but it keeps that stuff off while the power supply is ramping up, and then there's a delay time. Once the voltage becomes stable, now the thing's able to start running. So this is an important concept to understand because it's the circuit that can actually cause you a lot of problems, especially in Bally Stern games and things like that. Now, this is a really small amount of time. When we're talking about logic, we're talking about things that happen in extremely small pieces of time. So this would be from like 50 to 150 milliseconds. And I think that's about it. I could spend all day talking to you guys about this stuff, but I hope I covered some higher level concepts for you. I hope you're able to at least take a couple things away from it. I didn't have a lot of time for questions today, but if any of you guys want to come up and talk to me, I'm happy to talk to you guys. I've got some RAM adapters to give away as well. I mentioned those earlier. You can replace the RAM in your game with this adapter, and you will no longer need batteries. So thanks a lot for coming out, guys. I hope it was useful for you.